In this video, we're going to show that the magnetic field inside an ideal solenoid of length L with N turns and carrying current I is given by the ratio of the number of loops per length of the solenoid times the permeability of free space mu naught times the current through the solenoid. Now, to begin, we should note that an ideal solenoid is a solenoid that is very long compared to its diameter and consists of tightly packed turns of wire. If this is the case, then as we've shown previously, the magnetic field inside this ideal solenoid is uniform, parallel to the central axis, and the magnetic field outside of the solenoid is zero. Let's sketch our solenoid. So we'll have a solenoid. This will be an ideal solenoid, even though I'm not sketching it to look ideal. So remember, being an ideal solenoid, we are going to say that its length, which is going to be signified by capital L, is much bigger than its diameter, which we will signify by D. So we will say L is much, much bigger than D. Now, this solenoid has a current I running through it from left to right. So I, as it goes through each coil of this solenoid, we should indicate the orientation. So the X's indicate that the current is moving away from us at the bottom of each loop, and the dots indicate that the current is coming towards us at the top of each loop. So each of these loops indicate the direction that the current is going at either the top of the loop or the bottom of the loop. So from this perspective, the current is either coming towards us or moving away from us. Now, if this were truly an ideal solenoid, the diameter would be much smaller and the length would be much longer in comparison to the diameter. So we are exaggerating the dimensions here just so we could get a better perspective of what we have to do and the information that we have. Because this solenoid's length is large or long in comparison to its diameter, we know from what we've done previously that the magnetic field is uniform within the volume of the solenoid. And this magnetic field is parallel to the central axis of the solenoid, and the direction is given by the right-hand rule. So here we see that the magnetic field is oriented to the right. Now, outside of the solenoid, the magnetic field is equal to 0. So let's distinguish the magnetic field outside of the solenoid. I'm going to just call that B sub O for outside instead of B sub I. And for inside the solenoid, I will call it B sub I. Now, our goal is to develop an expression for the magnetic field. We're to show that the magnetic field is equal to N over L. So we are saying this solenoid has N turns. It has a length of L times the product of the permeability of free space times the current running through the solenoid. Since the magnetic field is uniform inside of the solenoid and 0 outside of the solenoid, we could create an Amperian loop to take advantage of that fact. An Amperian loop, remember, is a mathematical closed loop in space along which we're going to integrate. It's a path, and we're going to integrate the magnetic field along this path. Now, the Amperian loop that would be a natural choice for this solenoid would be a rectangular loop. So let's illustrate this rectangular loop in our picture. So let's take a portion of the loop parallel to the magnetic field inside the solenoid. So this rectangular loop has an orientation that is counterclockwise, going down from outside the solenoid to inside the solenoid. Once within the solenoid, it is parallel to the central axis of the solenoid, which is also parallel to the magnetic field. Then it leaves the solenoid, and then it circles back around to complete the loop. So here's our Amperian loop. And the reason why this loop is important, it's because Ampere's law says that when we take the line integral of a closed loop, that the result is equal to the product of the permeability of free space and the current if the vector that we are taking the line integral for is the magnetic field. And this I is actually the I that is enclosed by the Amperian loop. So in other words, the current that crosses the plane of our Amperian loop. So based off of this, we actually have 4 segments of this Amperian loop that we have to integrate. I am going to draw our Amperian loop over here, and we will call this bottom section segment 1, the vertical right section segment 2, the horizontal top section segment 3, and the vertical left section segment 4. Let's also illustrate our magnetic field. We know that our magnetic field along segment 1 is to the right because segment 1 is inside the solenoid. We know the magnetic field on segment 2 will start off being inside the solenoid and ends up being 0 once that segment leaves the solenoid. We know on segment 3 the magnetic field is equal to 0. And we know on segment 4 the same kind of thing. And I'm going to just write this as B4 is equal to 0 at the upper part. And we will say B4 is going to the right at the lower part. And I'll call this B4 prime to signify the difference. And B4 prime is just equal to the magnetic field inside the loop. And for consistency, I'll call this vertical segment on the right, this portion of the magnetic field, I'll call it B2, and this portion of the magnetic field, which is 0, once it leaves the solenoid, I'll call it B2 prime. Now, the reason why it's important to indicate the magnetic field along each segment of wire, it's because we are going to integrate the magnetic field on each of those segments. This Amperian loop, this line integral, can be separated into 4 integrals. An integral of the magnetic field on segment 1, plus the integral of the magnetic field along segment 2, plus the integral of the magnetic field along segment 3, plus the line integral of the magnetic field along segment 4. And we know that this must be equal to the product of the permeability of free space times the current enclosed by our Amperian loop. Now, looking at the current enclosed by our Amperian loop, judging from our picture, we have 4 current elements inside of our Amperian loop. Now, this Amperian loop could be of any length, carrying any amount of current. So we're going to need to be aware of that. Let's give ourselves a little bit more space to work. I'm going to move this line of work down a little bit so we could unclutter our picture. Now, in our picture, this segment of wire that that we are using has a length equal to lowercase l. And let's also say that since we know that the segment of wire can be of any length, that means we could contain any number of current elements crossing the Amperian loop. So I'll represent this number of current elements going through our Amperian loop as n prime. Notice that along segment 1, the magnetic field is in the same direction as the Amperian loop. Since it's in the same direction as the Amperian loop, the angle between the magnetic field on segment 1 is equal to 0. Knowing this allows us to use the alternative definition of dot product, being equal to the product of the magnitudes of each vector, in this case the magnetic field along path 1 and the line element along path 1, times the cosine of the angle between them. I'll go ahead and, for clarity, use a subscript to represent the length elements on each of the segments of wire to just emphasize that we are only integrating along that segment of wire. So for path 1, theta is equal to 0, the cosine of 0 is equal to 1, and this gives us the integral of b1 dl1 for the line integral along path 1. Along path 2, let's look at that. Path 2, notice that the path is perpendicular to a portion of the magnetic field. And then at some point along path 2 leaves the solenoid, and we know the magnetic field will be 0 after it leaves the solenoid. Now, if we look at this bottom segment in which the path 2 is perpendicular to the magnetic field, we can say that the angle between the magnetic field and path 2 is equal to 90 degrees. So here we have that our line integral integrating along segment 2 will either be equal to 0, because the dot product of 0 and our dl element will be 0. So it'll either be equal to 0, or the integral of b2 cosine of the angle between that portion of the magnetic field along that line segment 2. But as we see that the angle between the magnetic field and that line segment is 90 degrees, and the cosine of 90 degrees is 0. So this entire second integral goes to 0. In other words, the line integral along path 2 is equal to 0 because the magnetic field is either perpendicular to the path or the magnetic field is 0 along the path. Now let's look at path 3. Path 3 is horizontal going to the left. But path 3 has a magnetic field equal to 0. So when we write the line integral along path 3, since the magnetic field is equal to 0, this third term is equal to 0. And finally, looking at path 4. Path 4 is going down, going back into the solenoid, and at the upper part of path 4, the magnetic field is equal to 0. It eventually crosses the solenoid and goes inside the solenoid, and when it does, the magnetic field is uniform and to the right. But here, once again, the magnetic field is equal to 0, or the magnetic field is perpendicular to path 4. This means that we could write that the line integral of the magnetic field along path 4 and path 4 will be equal to 0, because again, either the magnetic field along path 4 is 0, or since this is a dot product, and the dot product contains the cosine of the angle, and since the angle is 90 degrees, we know this cosine is going to evaluate to 0. This leaves us with just a single integral, the single line integral inside our solenoid. So the product of the magnetic field along path 1 and the length along path 1 is equal to the product of the permeability of free space times the current enclosed by our entire Amperian loop. Let's redraw our Amperian loop and the current going through it. So we had our Amperian loop, which was a rectangle, and we indicated that we had currents coming towards us from each of the loops of our coil. We had said that the amount of current coming towards us is given by the n prime number of loops. This means that the total current enclosed by our Amperian loop is equal to the number of loops that passes through the Amperian loop times the current, since each of these loops has a current I in it. And don't forget that the length of our Amperian loop, we said, is L. This means that we could write that our integral along segment 1 is the integral from 0 to L of our magnetic field along path 1. Remember, our magnetic field along path 1 we are calling BI times dL1 is equal to mu naught times the current enclosed by our Amperian loop. And that current enclosed by our Amperian loop is N prime I. Now remember, the magnetic field is uniform. And since it's our only surviving magnetic field, I am going to call this B. And being uniform, it's a constant magnetic field, which means we could pull it outside of the integral. So the integral of the left side becomes BL1 integrated from 0 to L, and the right side just remains mu naught N prime I. Well, when we evaluate the limits of integration, we end up with just BL is equal to mu naught N prime I. And rearranging this, we get that the magnetic field is equal to N prime over L mu naught I. So this is the number of loops per unit length. The number of loops per unit length is a loop density, if you will. And if the number of loops per unit length is constant, we could rewrite this loop density as being equal to the total number of loops in our solenoid over the total length of our solenoid, which can be defined or equal to the loop density lowercase n. So this means now that the magnetic field inside our ideal solenoid is equal to N over L mu naught I, which can also be expressed as n, lowercase n, for the loop density, mu naught I, where capital N is the number of loops of our solenoid, capital L is the length of our solenoid, and I is the current in our solenoid.